Thank you very much, colleague from the fields, and I'm very pleased to present you the next speaker, Dr. Kang. I thought I know Yuan a long time. When I today tried to prepare how to introduce her, I found I don't know her. And when I went to the homepage, I found her funding sources come from everywhere. National Security, from Institute Agriculture and Food and Agriculture, from NSF, of course, and a lot of partners. I think the title of her talk probably explains everything. So yeah, she is really looking for the mathematical modeling of complex adaptive systems. Thank you.
Parts for today's talk. First, I would like to give you a little bit of kind of introduction of what do we mean by complex adaptive systems. So we use the CAS for short, and then we're going to focus on the social insect colonies as an applications, but also we briefly mention the application we have been applying to the human society. And then we're going to the part 2, talk about how these apply to specific case to see how the task organizations impacted by the metabolic rate, and then also by the colony size. And then the last part, we talk about the honeybee populations and how the parasitism and then the climate change, more specifically in this case, the seasonality impact their population dynamics. So, okay. So what's the CAS? So here show 3 examples can actually, for example, this picture is the web links. You can see the web links every day, they pop up or disappear. So the as itself can be considered as the CAS, and also there's the human and then the technology interactions, and then this can be considered another type. And then also the social insect group. So in general, so the properties of CAS, they have multi-scales. So for example, for the ant colony individual, it can be 1 level. Each individual belongs to a task group, that's the 2nd level. Also the colony itself have many different groups, and also the colony and 2 colony, right? And also there's emergent behavior. So for example, let's say in a social insect colony, each individual, they have their own preferences for the food. Some may prefer protein-rich food, some may prefer the carbohydrate-rich food. But as a colony level, right, how the colony itself achieve the goal to seek what kind of food will be more appropriate for the colony function for its growth. And then also there's another important is adaptive. So this is for example, let's say in the honeybee populations. So you have a nurse bee, which is staying inside the colony to taking care of the larvae and then the queens, and also you have an older age, the workers, they're doing the foraging. So if we in the situations, environment change, the colony require more nurse inside the colony to take care of the queen and then the larvae. So there's the scenario, basically some workers originally performing the foraging behavior, the task, they will be revert back to the doing the nursing. So they are adapt in a sense the role of their task. So the examples of the CAS also in this morning, Jane mentioned the immune the system, and also our brain, and also social insect colony, which I will talk more in details, and also our human society. So what are social insect colonies? There's many examples like the ants, wasps, bees, and then termites. So they have fascinating the social organization inside the colonies, which is reflecting our own society's complexity and also the cohesion. So there's 3 distinct characteristics here. So one is the reproduction of the division of labor. So what does that mean? Is not everybody has opportunity to reproduce, only the queens or kings, and sometimes you have a special class, they are able to reproduce. And also they're cooperative. So usually the workers are female, so they form different task group, and then they collaborate with each other to make sure the colony is functioning. And also, of course, there's overlapping generations inside the colony. So the why we're interested in the social insect colony also not only they are, but have this kind of fantastic the properties as the Kangs, but also they have the ecological dominance. So for example, the biomass is the 1/3, right? And then also the species number is way higher than the marine species. But for some species, such as the honeybees, they're also very important as ecosystems because as the pollination, and also they have very important economic values. So they're attractive also as the caste systems, is they have very resilience and robustness. Right? So for example, when we say the robustness is, if you have a colony with 300 members, if you suddenly remove 100 of them, right, and then the colony itself is quickly resemble itself, such as make the colony functioning again. So because of there's so many great property or the functions of the social insect colonies, such is not the interest is not in the biology, but outside in epidemiology. So for example, how the information transferred and virus transmitted inside the colonies, and also have been interested in the robotics. So at ASU, we have a great research group in the social insect area. So we are lucky to over the years have close collaborations with different labs. So we have so recently we published a paper in the social hierarchy. In this case, we talk about how the social organization change. When the queen is going to die, already die, you have a new classes member, from the worker, how they kind of become a new, as a new class. They take the job of the queen. Because of time, I'm not able to talk about how the social interactions with information and values. This is something we really have been doing greater results, both from the experiment and then the modeling, to capture how the information transmit inside the colony of the ants. And then we have trying to mimic this into, for example, to apply to epidemiology in the sense of, for example, right now we have COVID. So if we are interested, we can talk more after this. This one is what I'm going to talk about in the second part, talk about how the metabolic rate and colony size, and also the environment, in the sense if you have this kind of perturbation and noise, how to impact the task organization. And then we also have been working on the colony, the migrations. I think Gabby is here. I think and then I was going to mention briefly about your talk I think on Friday or Thursday afternoon. So we has been also closely working for the honeybee. So this is the a lot of work we has been working with, I think the Dr. Gloria DeGrani Hoffman from USDA, and also at ASU we have working with the Jennifer Phil and John Harrison's lab, and then we trying to apply mathematical models and depending also combine with the data to integrate the disease, parasite, the internal organizations of the colony, and then the nutrition, have a better understanding, what's the mortality and also healthy status. So the students not only just doing math model, but also they required to be part of the experiment designs. And then at ASU, they have these courses open to everybody, especially for bees. I think we have two, there's a Kami, he was already graduated, so he's now the NIH fellow. And then June, I'm going to talk about, she's going to graduate, but she has been working on a lot of the bees projects. And I'm going to talk about the work she's going to do. Actually, it's my third part of the, okay, just give you a snapshot, show you the model we are going to talk later. It's the model itself formulation is relatively simple, but the dynamics is really rich. And I think one of the purpose here is that, so many experts here, especially, for the OD and non-autonomous, hopefully there's some questions, hopefully you can helping us. So this is Gabby. I think she has been also working on the stingness, applied this, using the stingness bee as an example to try to understand the collective defense mechanisms of the of the social insect colonies. So she has been developing the Philipop systems to integrate to 3 different timescales and to understand the decision-making and process of the defense mechanisms in the colony. So I'm going to stop here. So, so she's going to talk more in detail about this project. And then the complex depth system, not only for the social insect, of course, for our human society. The one simple example was some team dynamics, right? So for example, right now I'm talking here, how I deliver the talk, it's very adaptive. It depends on my experiences, or also depending on each in the audience. You have different, you expert this, also you have your own, the experiences and your own style. So this is itself is for the compact adapt systems, but more in a general, the setting is this is something I have been working with the psychologist Nancy Nia from ASU, and then Jason from Army. We trying to understand trust dynamics. So to me, it's fascinating. And for trust, I think that trust is the fundamental of any relationship in our human, also in institutes, right? Also our countries. But what's the trust? To me, I don't have a clear answer to that. I have doing a lot of review as it was the trust in psychology, in social science. The definitions all over the place. So then we also have a lot of data in this area. So we just come down to the basic, which need to define as a mathematician, right? We like to define things and make things more precise. So what's the trust and how to measure it, right? And how to improve trust into have a better team dynamics. So under this, the umbrella, we're trying to use in both approach of the nonlinear dynamic systems and the machine learning the techniques, because you have so many data, we need to have both sides to working together. So as a subset of this project, I think the Lucero and I think the Carlos and has been working on the communication, because communication is also a very important component of the trust dynamics. So for the Army, they're really interested in the interactions between the human and autonomy or automation in general, because the most advanced technology has been the first used in the Army. So in this case, they have the experiment data, as you are able to see. This is I think the dots is the data, and then they will have a feeding. So this is we try to say 2 agents interact with each other. One is the human, one is the robotic, try to see how you communicate with each other. So they want to apply in a soldier, right, in the combat field. In a sense, how do you choosing if you're different personality, how do you choosing two persons such that you can make a better team? Or when you form a team, how do you improve a team to be better? So this is something the Lucero has been based on this, developing a discrete time model, and then she's going to talk more, I think, on Friday morning. All right, so I'm going to go to my more detailed explanation, the examples of regarding how the task called educations in the social insect colonies. So this is a recent publication in the JMB, the collaborations with the Dr. Fang and Chu from China, and then also the cell biologist, Dr. Champonnay. Right now, he's a professor in the U of A. So before I continue, I'm going to give a little bit kind of the introduction of the terminology we are using in the paper and in the talk. So first is a division of labor. So what does that mean? So basically, they describe the degree of the ends, they special on a certain task. So for example, if the one ends, they always doing one one task. If it's the same for all the members, and we say this definitely the police colony, you achieve highest the division of labor. Associated with that is a task allocation. So basically is how many ends or how many members or how many bees doing particular task. And then the task activity levels, this associated with the metabolic rate. So if you have intense of the perform certain work, in general, the metabolic rate may be higher or maybe lower depending on the particular task. And the experiment data suggests for different tasks, you may have different the metabolic rate. Some will be greater than 1, some will be less than 1. Right, so the motivation behind this project is because we task allocation and division of labor. These are very two extreme important features of the the social inside colonies, such that they are able to determine their behavior. So there are mathematical tools trying to show the colony level patterns, right, from the simple interaction rules. But many mechanism models we are observing have been based on the simulations, which is also very important for us to understand, understand certain phenomena. But many times the mathematical is not attractable, and so for this topic, they have also lacking to connecting the task switching, also the bulk rate, and then the colony size. So we're developing a simple model in hope to address the question like how the work activities or the task allocation in general has that's been distributed in the dynamic environment related to the metabolic rate and as well as the colony size. And also we looking at the particular developing stochastic differential equations to see how the environmental noises impact the task allocation or work effort in our application. So first, how we do the model. So all the tasks we have a demand, right? So the demand. So we assume the colony have more than one task. In the case you have only one task, basically, so you either work or you don't work. And also you have more than one members. In the case you have only one member, in this case, which is this is applied to the founding stage when the queen itself established a colony. So at the beginning, the queen she does everything on her own. So in this case, you can consider each xi is how much energy you allocating to different tasks. So the xi is depend the ratio of workers or the ratios of work effort. X0, this is the particular case when you don't do anything. There is sometimes they call lazy ends. Or in the case also consider the resting effort. So the summation will be equals to 1. And each of the demand D0 is basically we can assume either you are constant or which is depending on the colony size, or you can assume it will be linear increasing function of the working effort. So in the case of the specific task DI, so this is how we connect it into the metabolic rate. So this is the demand depending on the colony size itself, also the metabolic rate delta I, and then minus whatever the task has been performed. So n times xi is the population of the task group, and alpha I is indicating your effort intensity of the average of the for that task group. So we also have this kind of the relative stimulus for the resting or inactiveness. So after we have the demand, and then we say how we allocated the work force to finish to perform the task. Right? So theta I here we corresponding to the average response threshold for each task. So the larger theta I, which means you are less sensitive. The smaller value is more sensitive. So for example, if I'm living with a roommate, right? If there's a dish in a sink, right? You know, I'm a messy person, so when I see it, I just walk by. And if my roommate is a particularly nitty person, so when I see the dishes, so she has to finish it, right? So her threshold is very low. So in this case, we define that based on the demand D, that's for the task dk divided by the threshold theta k. This is measured the relative stimulus for the task k. And then from here, we are able to define the recruitment ability for the certain task I, right? So basically the product of the stimulus and an available worker to perform the task. And then you can divide by the summations, and then this is the recruitment ability. So from here, we are able to define the work allocation of the I depending on whatever the other group, right? You transfer to this group, right? Because they are the ends or the bees, they will communicate with each other such that depending on the needs of the colony, they will they may switch in a task. And minus whatever you switch into other task. and then after the some kind of the calculation, we are able to form this simple equation. And then now we have this kind of the full model, xi and then di. So we are expecting using this model to predict the colony size, the work allocation, and then the metabolic rate will impact the work effort xi for each task. So it's for the demand, sometimes also for each task, it depending on the environment. For example, the temperature or the humidity, right? For example, honeybees, if the temperature is higher, you need more the workers to foraging the water. So the environment can have a big determinations in the demand. So in this case, we're also adding the noise to see how this may impact the dynamics. So we have the more complete the results for the general model, but in this case, we try to apply to particular example. And so in this case, we're doing a little bit of modification rather than the threshold is fixed, but we're also using threshold is changing. So it is basically what it says is if you're doing the work, you'll be more efficient at it, and then you're more likely to work on this task. And then how you are changing or modify the enhance your response, decreasing based on the value of B. So from here, we have this kind of 2D model, X, whether determine whether you work or you don't work. It's the demand. And then from here, because only in 2D, so we're able to study dynamics in a more complete sense. So here we are able to show that the phi here is basically the demand for resting. If a resting is you don't, when it's less than a certain threshold, the colony will work all the time, and this is global stability. However, if you the demand for resting and then you above certain threshold, and then you have two scenarios. This depending on the size of the colony. If the colony is mature, if you're greater than the certain threshold, and then you have the existence as locally stable equilibrium point. Otherwise, you'll be go through a Hope application. You have this kind of stable limit cycle. So to address our questions asked earlier, right? So what's how the colony size, how the metabolic rate impact the work effort? So in this case, we instead of giving you theorems, I just using the diagram to illustrate our results. So the x-axis is the resting demand. X is basically workload. Here it says if the population colony size is small, it's very small. You are not mature, and then you have this 3 scenarios, and each suggests that when you increase in the demand, actually you're going to destabilize the colony. On the contrary, if you have the mature colony, and in this case, basically you are just only 2 scenarios, either you work all the time or you have you're decreasing as the demand for the resting increase. So this is actually this also we have finding the corresponding biological example to our theoretical work here. And now we want to looking at the metabolic rate. Again, we divided into 2 situations. We are able to find this kind of the relation from our the theorem. So now we looking at the population size. So the blue one is stable. Sorry if I didn't explain earlier. The red one is that go through Hope application. You can have a stable limit cycle in this case. So it suggests if you have a larger the metabolic rate for working, and then when the increase in the population size, actually you are able to stabilize the working effort. On the contrary, if the metabolic rate is not so large, in this case, you observe actually the destabilization happening when the population size is in the intermediate range. And this is also we're looking at how the enhancement measured by the B impact the population dynamic. This is basically can go through all 4 scenarios. you would be small, you are stabilized, and in the middle value, you have this kind of bubbling, you have this kind of limit cycle, and then you will become stable again, and then if it's so huge, so which means you are really very sensitive to work, which means you want to work all the time. You can consider this a workaholic, right? So that will be the region A4. So now corresponding to the three dynamic we observe for an ODE, now we want to understand how may the environment, let's say the noise in the demand impact the dynamics here. So in this case, we base on a simulation, based on the three scenario. Either you have a global stable, either all working all the time, or the interior equilibrium point, or you have a hub application, and to see how may given level of the noises level impact the allocation of the work and or the demand. So from here, we are the first column is basically average. I think probably about either 500 or 1,000 replicates. On the right is the distributions of all these the simulations. So in average, we can see the increase in the noise. This is the yellow part. You can see when without noise, yeah, 1. But when you increase the noise, you can see the X, the effort decreasing, but the demand is increase. Right? So we're looking at the second class when you have the interior equilibrium point, and then we see the similar. Your noise actually the decreasing the work effort by increasing the work demand. And the difference is in previous ones, distributions of the work is more look like the normal distribution. And then for cyclic original, you can have this kind of very regular ones. This is interesting. When you add in a noise, actually it seems in average you decreasing the amplitude of both work and the demand, but in average itself is the X still decreasing, the demand is increasing. So this is something we observe, but we are not able to show it theoretically. So if any of you have some ideas to explain why from theoretical point of view, we are able to prove this, that would be really appreciated. So the next step is we want to connect into the data. So this is actually we observing from the many colony. I just give you 2 examples, the large one and small colony. This is X is the time in seconds, so 300 seconds, which is 5 minutes. X is basically you mark everybody, and then you say who is doing, who are working or not. So it's very label intensity. So we able to calculate it for different colonies at different level. You can see the patterns. It's indicating the model. Indeed, you may want to including the stochasticity there to have a better fit. So the summary here is basically we are developing this model to looking at how the colony size, how the metabolic rate impacted the task allocation, and then also the stochasticity, and then more work are needed in this in this area. All right, so I'm going to talk about the honeybee. I want to see the parasitism in this case is a particular mites. The size of mites is here very small actually. And then also the seasonality. So this model, the honeybee parasite model. So the parasite here is depending on the mites. Parasite depending on the honeybee. So this part particularly indicating the probability of the mites attaching to the honeybee, so that they are able to reproduce. Right. So if there's no mites, actually itself is just this part. And this part is different, the dynamics different than normal logistic growth. It has the strong adding effect. And then we are looking at this model to address 3 questions. So well, how does the seasonality impact honeybee population? And second is, let's say this constant environment, how the parasitism impact the population of the honeybee. And then also we're looking at the combined impact of the seasonality and then the parasitism. So these are joint work with the Harrison lab and also Hoffman lab. So the seasonality in this case, we're looking at the egg laying rate of the queen. So only queen will laying egg. All other workers, they don't lay egg. So the seasonality here, obviously the reason of this is because you have the food, the resources, temperature, and whether they're changing over time. And then the model here, we using the cosine function, and then I will explain in the next slides why we're using this one. So in this model, in these equations, we have the epsilon indicating the intensity of seasonality. Gamma is the length of the season, and then phi is the timing of the queen laying the maximum egg. So from here is this is the coming from the both. One is from literature. I think back in the 1980s, I think Gloria, our collaborator, and she has this model and then data to suggest the queen laying his follow this distribution and follow this equation. And our recent data coming from the experiments on the peptides in the Harris's lab, and then when we're doing the data feeding, actually also observing this is the dots is the data, the blue is the feeding, and then indicating this seems to be the right equations to describe the seasonality in a queen eggs laying. So because original model we have so many parameter values. So as a mathematicians, we want to reduce the parameter values as much as possible. So we are able to eventually to reduce in as a UV these two equations, but we still have the K, we have the D, the mortality rate, and then the it's kind of predation. If it's paraseason, in this case, you can consider predation and omega. So we're able to show for the non-autonomous models, you are able to exist unique solutions, which is positive invariant and bounded. And we're able to show the egg laying rate be too small, your whole colony going to collapse, which is not surprising. In the case if there's no mites and the egg laying rate is not so small, we're able to show the survival of the honeybee. It's under condition, the initial condition is large enough, because you have the strong allele effect in this case. So now we're looking at how the seasonality impact the honey population. Right now we only have one equation here. Right? So basically, if this R bar is the constant, basically the dynamics is very simple. So as long as the initial conditions is above certain threshold, your coexistence is equilibrium point or your extinction to 0. Now we let the RT as a function described by this periodic function. So we look at this is basically its initial condition, the H0 or the H is U0. So the blue basically is the initial conditions and epsilon value such that you colony collapsing. Otherwise, the red is you are survive. So let's using this example, like phi equals to 0, gamma equals to 4. We are able to see there's no seasonality. If there's no seasonality, actually the straight line, the white line here, or the left, you collapsing on the right, you can survive. But here is you can see there's some initials. If there's no seasonality, you're collapsing, but after seasonality, you are able to survive. Right? So basically, in this case, you're indicating the positive impact coming from seasonality. But that's not always the case, because also depending, for example, the similar. In this case, actually, is the negative impact, and you can see the black line. They are causing the blue regions. And also, if the gamma, the length of season is large enough, we're able to show that large actually is always collapsing. The large intensity of seasonality collapsing. Right. So as a summary is basically the seasonality on the impact on honeybees, it depending on the length of the seasonality, and then also the intensity of seasonality, as well as the timing of the queen laying the maximum number of eggs. And it can be positive, it can be negative. Usually we are able to, in this case, we're able to do more say, for example, in the cases, depending on the period, if the phi less than gamma over 2, usually you have a positive the impact for seasonality. So now we're looking at the only seasonality, without seasonality, but they have parasitism. Now we are actually just 2D model again. And in this case, we are able to study the dynamics completely. You have a 4 scenario, either the colony collapsing or only bee survive, or the coincidences. The coincidences is divided in 2 cases. One is the local stable, because 0, 0 is always local stable as well. You have multiple attractors. And then, but the interior equilibrium point can be destabilizing. So in this case, basically, by comparison, we're able to say parasitism actually in general is a negative impact. Either you make colony collapsing, or you are able to lead coexistence by the population decreasing, or destabilize system. So how does it destabilize? And we are able to see the based on the parameter values. You can go through 2 different sub or supercritical applications. So for example, in this case, we're choosing particular case. When the K is small, actually it goes to the subcritical application. The red one is the case when you are doing the supercritical applications. So either parasitism also in a negative way impact on population, either you have the stable limit cycle, or actually you collapsing the whole system. So now we're looking at this, the synergistic impact of parasitism and seasonality. So at this point, we are looking more, we want to see the dynamic patterns, and also the how they impact the basin's attractions. So in this case, I just give you some examples we're observing. In this case, is the red one is the coincidences, the blue one is the collapsing. So this is actually is just the basin's attractions. Axis is the honeybee initial population, Y is the parasitism populations. And we're able to see actually, again, so this the situation will become very complicated. This is the case when when there's no seasonality, you have coincidences. And now when you're adding a seasonality, and depending on the gamma, phi, and then epsilon value, sometimes you are really bad because the coincidence is really strongly decreasing. And sometimes you may be good. So for example, originally you don't have some, the red area, now you have red area, which means you're able to coexist. So it can be good and it can be bad. In the case if original no seasonality here, you have the limited cycle. And then when the gamma is small, it's just shape is similar. But if you are increasing the gamma value, and then you can see the basin's attractions can be kind of fractal. So in this case, again, very complicated. We trying to it's ongoing work, and we're trying to see whether there's any kind of theoretical work we are able to have better classification of the impact of the seasonality. So if you have so many experts here, if you know any kind of references, we are able to to have more to the tools for us from a theoretical point of view to study dynamic patterns and the basin attractions for this type of model. I really appreciate it. So I think the take-home message is basically we summarize the seasonality is can be positive, can be negative, right? And the parasites in general is the negative, but if you combine them, then it can be even more complicated. But there's right now we do have this experiments designed. They try to understand how the temperature actually impact the population dynamics of honeybee. But of course, more theoretical work are needed. So I think I'm going to stop here, and I will take in any questions you have.